Today we're going to learn about Baskin's equation and how to predict the cycles to failure for a given problem. Now, our stress life method is used for high cycle fatigue. Generally, high cycle fatigue is defined anything that is greater than 10 to the 3 cycles. However, the usefulness of Baskin's equation sits between 10 to the 3 and 10 to the 6 cycles. This is the region where on a log-log scale, our data tends to have a linear type relationship, right? Now let's introduce Baskin's equation. On a log-log scale, a power function is linear. So Baskin's equation is a power function where the stress amplitude is equal to a constant A times cycles to failure to a constant B, right? And where if we know our material constants A and B, we can rearrange Baskin's equations to solve for the cycles to failure given any particular stress amplitude. Now, how do we determine the A and the B material constants? Well, let's note that on a log-log scale, a power function is linear. So if we were to draw Baskin's equation, it is a straight line where the slope is equal to the constant b, and the intercept on a log scale is equal to the constant a. Now, since we're defined between two regions, 10 to the 3 and 10 to the 6, we can use those to calculate our slope, and they can also help us to find that a parameter. When we do so, we can determine that a is equal to S1000 squared divided by SE, where S1000 is the stress amplitude or fatigue strength at 1,000 cycles. We can also find the slope B is equal to negative 1/3 times the log of S1000 divided by SE. Again, where S1000 is the fatigue strength or stress amplitude at 1,000 cycles. Now, let's actually look back at this plot to just get that in our minds. This point right here at 1,000 cycles has a stress amplitude of S1000. And this point right here at 10 to the 6 cycles, that's our endurance limit, below which we have infinite life. So these 2 points, if we know these 2 points, we can plot Baskin's equation. We find A and B, and then we can start making predictions on cycles to failure. Now, how do we find S1000? Well, there is a tool that we can use to find S1000 where we can assume S1000 is equal to some factor F times the ultimate tensile strength of our material. Now, if we were to do many hundreds of experiments on many different steels, which is what was done, we would find the following equations for that F factor, where the F factor is some polynomial in terms of KSI units, and it's a different polynomial in terms of metric units. And where F has a threshold, F is equal to 0.9 if the ultimate tensile strength is less than 70 KSI, which is 500 megapascal. So using this empirical equation, if we know our tensile strength, we know our S1000. Right? Now, if we want to plot these polynomials, we'll furnish the following plot of that F factor versus the ultimate tensile strength and the 2 sets of units. You can see that it kind of hardens down, and then once we get to a certain point, we're kind of stuck at a critical value. Now, another thing we need to consider is the endurance limit of the material. How do we find that? One thing we can do is we can estimate the rotating beam endurance limit of our material. This is the endurance limit that is fully reversed from the Euler experiment. So if we do many hundreds of experiments on many different alloys and steels, we develop the following plot where each dot represents the ultimate tensile strength versus the endurance limit for a different steel combination or wrought iron. So each of these dots represents many hundreds of experiments. When we look at the relationship between ultimate tensile strength and the rotating beam endurance limit, we can see that on average, there is a 50% relationship between them, that they are about half of each other's value. There are some lower and upper bounds, of course, but if we just want to have a generic term, 50% seems to be pretty reasonable, up to 200 KSI. So, for steels subject to completely reversed fatigue, we can say that that rotating beam endurance limit is equal to, in brackets, half of the tensile strength. If the ultimate tensile strength is less than 200 KSI or 1400 megapascal, and we can set it to a fixed value of 100 KSI or 700 megapascal if the tensile strength is greater than 200 KSI or 1400 megapascal. Now, important thing to note is that this endurance limit that we found is the rotating beam endurance limit. This is under completely reversed fatigue conditions, the ideal Euler experiment. However, the endurance limit of real parts, of our actual parts, subject to specific loading conditions and geometry and temperatures, may be very different from what we find from the rotating beam test. And so what we're going to learn in the next series of videos is how we modify that rotating beam endurance limit to determine the specific endurance limit for our actual parts under the actual conditions they are designed to operate in. And that is called endurance limit modifiers. See you in the next video.